This is a video of our development systems from early 2012 forward. Going left to right are the older systems. In the back left corner are several of our infrared, long-wave infrared and low-light cameras on the tabletop. You can see a piece of white paper, some cameras on top. We have a family of long-wave infrared and also a 4K color camera. On the far right, quad-core PC104 on the tabletop, and to its right would be a 1024 by 768 lenticular display. That's an LVDS interface. Behind that would be it's a 4K, about a 28-inch LCD display. And the message here is that we have control over the Z-axis. The bottle is basically popping out of the screen. We of course are focused on depth perception, true to life perception, and that's what you see in the moving displays on the tabletop. We started off with degraded vision enhancing for operators of military vehicles. That's where the start was. So I'm going to do a quick pan and a close-up, and then we'll move forward. Our current prototype is a PC104 quad-core driving an LVDS, which is the LVDS 1024 by 768. We're using a long-wave infrared RS-170 NTSC long-wave infrared camera, which is feeding the video. Now this is a night drive, and the text you see is our effort to have timestamps and track the latency from camera glass to glass, glass to lens, glass to the display. As you look at this bottle, we have the program stopped. Hopefully you can see that there's some perception that the bottle may be kind of popping out. The message here is that the lenticular lens that we use, we can design them accordingly to allow for depth or pop. We're focused on true to life perception of depth. And then the message here would be we're using a passive camera, a single passive camera, where we're generating multiple rays for the eye. So it's monocular to binocular vision is where we're focused. This is the current platform packaged up. I'll show you in just a second. Our path forward is using, we've gone to Nvidia. To the left here is the Nvidia TX1. The one that's powered up is the Nvidia TX2. And the code has been migrated to operate on the Xavier platform, which is a 512 core platform. And all in an effort to drop the latency and to allow for plug and play algorithms that others might have for machine learning or artificial intelligence. You can see the numeric on the display. This is one of our efforts to do in tracking frames and timing of our platform. So going a little closer here, this is a new 12.5-inch 4K LCD display. It has dual display port and HDMI. We've got it frozen on a tank visualization. This particular display, we've moved fast forward with lenticular lens. We can make a lens as narrow as 10 microns, and that means we can go down to a 2.5-inch diagonal, all the way up to a 99-inch diagonal. And we have auto alignment developed for the manufacturing of this, and this is all NATO-friendly country development. We also have dashboard clusters and other things. So this particular display will be visualizing true-to-life imagery, as well as a mix of virtualization and dashboard clusters, driver information. Welcome to our prototype. This is the demonstratable prototype that we use. You see it's on kind of a tri-vacuum mount. We vacuum mount it to the windshield. The text you see, I'm actually driving the vehicle. This is a night drive in the Uwharrie National Park outside of Fort Bragg. We have several functions. We can do record, playback, a variety. This particular unit is designed for 4 cameras, but we only bring out 2 military circular connectors. We have USB, this is power, some fusing, actually quad-core i7s inside, along with our conversion from analog video to digital. This is how we built our prototype for demonstration, to have it kind of tightly coupled. We can plug it into the cigarette lighter jack in the vehicle, and we're running it. It's actually providing DC power to the cameras. All of our prototypes can switch between live camera feed. You can see me here, live camera feed, and record and playback. We can switch between, typically they're designed for 2 cameras, white hot, black hot, record, playback, a variety of options. We have 2 of these. These are actually, we used the same supplier a few years back to build these for us. They all have lenticular, 1024, 768 lenticular lens. And these are the first generation. They're mimicked after the NVAS5, almost exactly the same type of mechanical packaging. This is a battery pack, a portable battery pack. We can typically drive one of our units for about 4 or 5 hours with the battery pack. And these are our cameras. This is an Israeli optical long-wave infrared 760 NTSC RS-170, 30 frames per second. U.S. Army Special Operations Command have been using WATEC for low light, so this is a low light camera that we're using, similar to what some of the S&T guys are using at Fort Bragg. And this is a VUMI, also made by the Israeli company Opcal. So just kind of backing up, this is our lab environment. We also have in this building anechoic chambers with a SATA-MO ring. It's about a $4 million test bed for wireless capability, antenna development, etc. And 3 pop-up towers at about 106 feet. So thank you very much for taking the time to review our capability.